This is lesson 1.4, slopes using limits. The goal for today is to be able to find the slope of a secant and tangent line using the limits of a function. There's some practice questions listed here. They're also listed on the unit outline, and there's going to be an exit ticket at the end of this lesson, and it is posted to the VLE. You can give it a try once you've done the homework questions and you feel ready. In addition to teaching you how to do this, I'm also going to give you your first rule to live by for calculus, as I like to call them. This is the difference quotient, and this is an equation that you're going to be able to use to determine the slope of a tangent or secant line using the limits of a function. One word of caution when using limits. Finding slopes using limits only works if the function is continuous for every single point along the curve. The line passes through every single point. So if you can run your pencil along the curve and there's no breaks in that curve, then you can use this method. There can't be any holes or asymptotes at all for this method. So this top image is a graph that we're used to seeing. We've got a curve, we've got 2 points along this curve, we've got a line connecting those 2 points. And in math speak, what we've got going on is, given a point, P, at A, f of A, and Q at x, f of x, the slope of the secant, PQ, can be given by the equation slope, or m, equals f of x minus f of A, all over x minus a. And remember, f of x is just our y2 value for point Q, and f of a is our y1 value, that's the y value at point P, and x minus a is our x2 and our x1 values. So when we let Q approach P, so as this point Q gets closer and closer and closer and closer to P, x approaches a. So this x value here approaches a. It's getting closer and closer and closer to a. And we can see that the slope of PQ, as we get closer and closer and closer, approaches the slope of the tangent. So if I have my tangent line for this point here, this point here, this point here, and you can see as we get closer, we are getting very close to that slope of PQ being the slope of the tangent. Mathematicians have a way to denote the idea of the slope of the secant getting closer and closer to the slope of the tangent as x approaches a, and this is called a limit. Now, if we take a look at the equation for this with this x minus a on the bottom, I think we can see that x can't equal a. So we can't get all the way there. We just have to get really, really close. So if x equals a, then the denominator would be 0 and the expression would be undefined. So how do we write this? Well, we write it like this. The slope m is equal to the limit as x approaches a. So this x arrow a is as x approaches a. And then we have f of x minus f of a over x minus a. Just our regular y2 minus y1 over x2 minus x1. So let's look at an example. And this example says, determine the slope of the tangent line to the curve, y equals 2x squared plus 4x minus 1, at a point along that curve 2, 15. So 2 here is going to be our a value, which means 15 is our f of a value, or our y value. So a is going to equal 2. So what we want to do here is determine the slope as x approaches 2. So we're going to say the slope is equal to the limit as x approaches 2 of our 1 point minus our other point over our x values. So that's going to look like this. So we have 2x squared plus 4x minus 1 minus 15, that's our f of a value, all over x minus 2. We're going to collect some like terms here up in this top part. So when we do that, we end up with 2x squared plus 4x, and then negative 1 minus 15 gives us a negative 16, all over x minus 2. Now, we want to eliminate as much of this equation as we possibly can to make it a little bit easier to solve. And so we want to get rid of that. So what we're going to do here is we're going to pull out a greatest common factor, and in this case that would be 2. And I'm going to rewrite it with that greatest common factor pulled out. So m is equal to my limit as x approaches 2 of 2, and we're left with x squared plus 2x minus 8 all over x minus 2. Now, we want to get rid of that x minus 2 on the bottom, because remember I said we want to get this a value as close to x as possible, but they can't be equal to each other. So we need to factor this so that we can try and eliminate this x minus 2 on the bottom. And if I factor this, I end up with x minus 2 is equal to 2x plus 4 and x minus 2. That's convenient because that's what I need. So now I can eliminate those or cross those out. They cancel each other out. And now what we're going to do is I'm going to say, well, then my limit as x approaches 2 is just simply equal to 2x plus 4. And I'm going to substitute in my value of 2. So now I'm going to substitute this value into here, which gives me 2 plus 4. And when we do that math, that gives me a slope of equal to 12. So the slope of the tangent as x approaches 2 is equal to 12. Now let's talk in general terms. So if instead of having P and Q that have x and a values, now we have a point Q up here that has an x value of a plus h and a y value that is f of a plus h. And all that really means is that h is just the distance between the x values on the x-axis. So as these values get closer and closer, as h gets closer, as q gets closer and closer to p, the h values are going to get closer and closer and closer to being 0. So we can use this relationship in this shrinking h value to determine the slope by using our f of a plus h, which is our y2 value of this q point getting closer and closer and closer, minus f of a, which is our original y value of point p, all over that distance h. And this gives us the general equation for using limits to find the slope of a tangent as m is equal to the limit as h approaches 0, as those x's get closer and closer and closer together and h gets closer and closer and closer to being 0, of f of a plus h minus f of a all over h. And this right here, my friends, is that first rule to live by. This is called the difference quotient. And it allows us to calculate the slope of a tangent as h gets very close to 0 for any continuous function. What I would recommend you do with these rules to live by is start a separate piece of paper that you're going to keep with you throughout your lessons that has these rules. There's going to be lots of them coming, so this is going to be the first of many rules for calculus, but this will be your first one. So write down the difference quotient as it appears here. The slope of the tangent is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. Let's look at the last question again. So we have the function y equals 2x squared plus 4x minus 1. We have our point of 2 and 15, remembering that this is my a value and this is my f of a value. And now we're going to put this into our difference quotient. So my slope of the tangent as the limit of h approaches 0 is going to be equal to f of 2 plus h, which will be my y2 value, minus f of 2, that's my y1 value, all over h. So let's fill that into our equation. Everywhere there is an x, we're going to put 2 plus h in our original equation. So we have 2 times 2 plus h squared plus 4 times 2 plus h minus 1, and then minus our 15 value all over h. So what we need to do now is we need to expand, simplify, and collect like terms. So the limit as h approaches 0 is going to be equal to 8 plus 8h plus 2h squared plus 8 plus 4h minus 16 all over h. So now if I take a look at this, I can see that this 8 and this 8 total 16, a positive 16, which allows me to eliminate that minus 16. When I collect the like terms, that leaves me with the limit as h approaches 0 of 2h squared plus 12h all over h. So we need to get rid of the h on the bottom. In order to do that, we're going to pull out our greatest, we're going to pull a common factor. And in this case, the factor that we're going to pull out is actually going to be an h. So when we pull that out of there, we end up with the limit as h approaches 0. Pull out that h, and that leaves us with 2h plus 12 all over h. This is what we needed to have happen because we need to eliminate that h. Now I'm going to substitute my 0 into my equation anywhere there's an h, and that is going to give me the slope of 12, which we already knew. One last thing I wanted to share with you is this concept of Pascal's triangle. Some of you may have seen this before. It is a very handy tool for expanding binomials as they get to a higher and higher and higher degree without having to do all of the math. So as our functions get more complicated, the act of expanding and simplifying can become more and more difficult. This is where you can use Pascal's triangle to make it easier to expand those binomials. I've given you the basics here. Those of you that are familiar with it, this may be enough for you to jog your memory. For those of you that are unfamiliar with the use of Pascal's triangle to expand binomials, I've posted a video if you're interested, and that is posted separately to the VLE. And so, yes, so I tend to use this instead of expanding everything, but ultimately it will be up to you what you want to use.